Welcome to the lectures on design and analysis of algorithms. So we will continue our discussion on graph algorithms, and today we will look into shortest path algorithms, and the first one we will look into is called the Bellman-Ford algorithm. So we will define two problems. One is single source shortest path algorithm, and other one is all pair shortest path algorithm. So what is the input? Input is a weighted connected directed graph G is equal to VE, where V is the vertex set, E is the edge set, and the weights are nothing but function W on each edge E in E. So corresponding to every edge in the graph, we have a weight. Okay. Note that this is a directed graph. We are talking of a directed graph. Now, we have also a source node S in this set of vertices V. Okay. What we want to compute is, given this source node, the question is compute the shortest path from this source node to all the nodes in V. Fine. That's the problem. It's called single source shortest path. Okay. Problem. The other version of this problem is all pairs shortest path pair problems. So again, you are given a weighted connected directed graph, and the weights are nothing but given in terms of function W corresponding to every edge. There is a weight. You can assume that these are represented as a matrix. Okay, and your task is to compute the shortest path from all nodes of V to all nodes in V. Okay, what is the shortest path from between every pair of nodes? Okay, that is called all pairs shortest path algorithm. So today we will look into the first problem of finding shortest path from a given source vertex S. Okay. Now here I would like to comment that we will assume here that you can have negative edges. Okay, negative weighted edges. That means weights could be negative. So in certain algorithms, the assumption is that you cannot have negative weighted edges. So in Bellman-Ford, the assumption is that you are allowed to use negative weighted edges as long as there are no negative weighted cycles. Okay, so let's understand what does it mean. So if in case there are negative weighted cycles, you will notice that there are no shortest path. Okay, doesn't matter how you compute a shorter path, you can still compute a better shorter path. Okay, fine. So from a source S to node T, provided it comes in that cycle. Now, one thing I would like to point here, when we are talking of shortest path, what we mean is that we will look for a sequence of vertices, a simple path, such that if you add the sum of the weights of those edges, then that sum will be minimum. That's what we will call as a shortest path problem. Okay, it's now if you say that all the weights are same, it boils down to looking into the number of edges. Okay, the path which is having the least number of edges will become the shortest path. But if the weights are different, then the meaning of shortest path will be different. Okay. So if we disallow negative weight cycles, then there is always a shortest path that contains no cycles. Okay, fine. So if we are not allowing negative weighted cycles, then definitely we will have shortest path between S and any other vertex. In case there are negative weighted cycles, we might not have shortest paths. So let's understand that using an example. Here is an example. Now notice that we have in this graph, this is a directed graph, and we have the source vertex S, that's our source vertex, and we want to find what is the shortest path from S to say A. So you can see that the shortest path from S to A is nothing but this edge. Okay, so the total weight is 3. The shortest path from S to B is nothing but SAB, and the total weight is 3 minus 4, which is minus 1. Okay. Now look at the shortest path from S to C, it is 5. From S to D, it is, you can go from S to C and from C to D, so 5 plus 6, 11. Now notice that there is an edge -3. Okay, so if I go like this, S to C to D to C to D back, then what is the weight? S to C is 5, from C to D it is 6, from D to C it is -3, but from C to D it is 6. So total weight is nothing but 5 plus 6, 11, plus 6, 17, minus 3, 14. Total weight is 14, which is more than 11. Right? So the shortest path is S, C, D. Now look into this. What is the shortest path from S to E? So you can say that, okay, the shortest path is having weight to S to E. But I can show you a shortest path which is having even a lesser weight. So essentially it is a shorter path. Okay. So how? Let's say we say S to E to F back to E. What is the length of this path or cost of this path? S to E is 2, E to F is 3, F to E is -6. So that is -1. So if I keep on doing, say I go S to E to F to E to back to F to E, then I have S to E is 2, E to F is 3, F to E is -6, E to F is 3, and again F to E is -6. So this is 3 plus 3, 6. So this cancels out. This is -4. So more negative. And if you keep on doing like S, E, F, E, F and E, F, you will see you will still reduce the cost of the path. Okay. So your shortest path is having cost -infinity. You can keep on doing this S to E to F and keep on cycling. In fact, if you notice, this cycle E and F, the cycle is E to F back to E, is having total weight -3 minus 6 -3. So you can keep on cycling, and every time you cycle you reduce the total weight. Okay, so that's a negative weighted cycle we are talking of. Okay, so if you have a negative weighted cycle, then you cannot have a shortest path. Okay, I should not say you cannot reach, you do not have a shortest path. Okay, so if I do not have a shortest path to E, I do not have a shortest path to F either, or G either. I mean, they are all -infinity. Okay. So we want to assume that typically we do not have negative weighted cycles. If we have negative weighted cycles, then we want to figure out where they are. Okay. So now we will look into this Bellman-Ford algorithm, for which we will use a technique called relaxation technique. What is the relaxation technique? For each vertex V, what we do is we maintain an upper bound dV. What is dV? This is a quantity stored in that node V, which is an upper bound on the length of the shortest path from S to V. So from S, we can reach V via many other nodes. So V stores through which node should I reach to V such that I will get the shortest path. So I keep that in that dV. Initially dV, we say that it is initialized to infinity. That means I cannot reach to V. And then if I get an edge U, V, W in my shortest path, so U, I'm coming from U going to V, that's the edge, and the weight of that edge is W. If that's the situation, then what we can do is we can shorten the path to V by going through U. When can that happen? Can we shorten it? It will be only happening if I see that already the cost to V, if that is more than cost to U plus WUV. Then I can update, then I can say that, okay, through some other node, if I'm coming to V, the cost is more than coming through U. So what is the cost of coming through U? Whatever is the cost to reach U plus the edge weight UV. Now if that is less, strictly less, then we say that, okay, dV is going to be updated by du plus weight of UV. And that's what is called relaxation. Okay, and this can be done in order of one time. Okay, so what it is saying is that, let's say, I have from U, I have to go, I'm reaching to V, fine, and weight of V is say 100. Okay, so dV is equal to 100. Okay, let's say, and du is, let's say 20, and weight of this edge is 10. Then definitely the cost to come to U is 20, and then I have this edge with weight 10. Then the cost to go to V is going to be 20 plus 10, 30. That is going to be better. So I will update my dV to 30. Okay, that's what is the relaxation. And how much time it takes? Constant time. Okay, so let's understand what is the Bellman-Ford algorithm. You are going to work on a graph G. It is a weighted graph, weights are given, and you have a source vertex. You have to find what is the shortest path from source vertex to every other vertex. So first step is to initialize this graph. So we call a routine called initialize single source GS. What it will do is, corresponding to every node, we keep track of two things. What is dV and what is the parent of V, through which vertex I should come to V. So initially dV will be infinity for all the vertices. Only for the source vertex, because that's the starting point, distance to the source vertex from the source vertex is 0. And parent of V will be initially nil, and parent of S will be also nil. Okay, because that's the starting point. Fine, that's the initialize routine. Then what you do is, for I is equal to 1 to V minus 1, that means you are going to iterate it V minus 1 times. Okay, and in every iteration, what will you do? You will check every edge in the graph and you will relax it. Okay, so and that's what is essentially the main thing. You will do this exercise for how many times? V minus 1 times. What is the exercise you will do? You will take an edge, you will relax it. Okay, you will take an edge, you will relax it, all the edges in the graph. Then again I will be incremented to the next value. You will relax all the edges in the graph. I will be incremented to next value. All the edges in the graph will be relaxed, and so on. Okay. At the end, what you look into is, for every edge UV, if this condition dV is more than du plus WUV, if that condition is satisfied, that means there is a negative weight cycle. Otherwise, which means, if I keep on continuing, I will always keep on reducing my dV infinitely. Fine. In case if I do not have a negative weight cycle, I will never reach to this position. Okay, and I will have my shortest path from S to every other vertex. Fine. Okay, so let's look at an example. Let's solve an example and then it will become clear. Now notice that in every iteration, I from 1 to V minus 1, you are walking over all the edges. Now these edges are arranged in some sequence, in whatever sequence you have arranged it. Okay, so that sequence is going to matter. Okay, but overall it's not going to matter, because you are going to do it 1 from 1 to V minus 1 times. The reason is that you can reach to any vertex from S at the most through V minus 1 vertices, right? Total V vertices are there. Okay, so you can reach there through V minus 1 vertex, right, at the most. Okay, and what happens is, in every time, if you look into this link, every time you will update what is the shortest path, and gradually the right value will get percolated at the right position. Okay, so let's understand the example, then it will become clear how it works. So the edge sequence we are going to follow is AB, BC, CA, DC, ED, SA and SE. These are the edges for this graph. Okay. And corresponding weights are shown. So initially, as I said, I'm just tabulating it. Okay. And for A, the dV value, the first value is dV, so dA. Okay. And within parenthesis, I have kept pi A. Okay, fine. So this is dB, pi B, dC, pi C, and so on. So as I said in the initialization phase, all of them are set to infinity, parents are set to nil, except for the source node, weight, dV value is 0 and parent is nil. So first, your iteration starts, I becomes 1. So you are here. And now you start processing every edge in this order. So first edge is AB. What is the weight of A? Weight of A or dA is infinity. Plus 5, is that going to be less than infinity? Well, infinity plus 5 is no, you cannot say. So there is no point in updating the weight of B. Okay, so it remains at infinity, parents remains at nil. Okay, then BC. B is still infinity. Okay, because that's the value, infinity, the dV value. Plus 7, the weight is 7. So this is infinity plus 7. Is it better than infinity? For C it is infinity. Well, it is not. So there is nothing to be updated. Fine. For CA, again C is having infinity. Infinity minus 5 is, not better than infinity. So A is not updated. We go to DC. DC, again, this is also infinity. Fine. So infinity plus 3 is not going to update infinity. Okay. So D is not updated. So C is not updated again. Okay. Fine. We were at DC. Then we go to ED. Now ED again, E is infinity. Plus 2. Nothing is going to happen. So D remains at infinity. But then comes SA. Now the dV value of S or ds is nothing but 0 plus 1. So this is 0. Okay, so ds is 0 plus 1 is going to be definitely less than infinity. This is infinity. So E gets updated. The distance value or the D value of E gets updated to 1 and parent becomes S. Okay, for SA. Sorry, this is for SE. We should see SA first. Okay, for SA, what will happen? ds is 0. A is infinity. So 0 plus 3 is better than infinity. It is only 3. So it gets updated to, this one. Okay, 3 and the parent is S. So dA value is 3 and parent is S. Similarly, DE value is 1 and the parent is S. Okay, so we are done with all the edges. We are done with this phase. We increment our I to 2. So we again start. And this time, notice AB. Now AB, this is still, now AB, I changed A to 3, right? The value of A became 3. dA is 3 now. So 3 plus 5 is 8, which is better than infinity. So this should get updated to 8. So 3 plus 5 becomes 8. So B should get updated to 8 and the parent value is A. Fine. Okay. Then comes BC. BC, B is just updated to A. Plus 8 plus 7 is 15. So you update C by 15. 15 is better than infinity. Okay, lesser than infinity. Right? So you are going to update it to 15. And what is the parent of C? B. Fine. Then comes CA. Now when you come to CA, CA is having the weightage -5. But what is the value of C? C is 15. What is 15 minus 5? Is 10. Is 10 better than 3? Is it less than 3? No. So nothing to change for A. So A remains at 3. Okay. Fine. Yeah. A remains at 3. So we are talking of CA. Right? Okay. Sorry, this will be S. That's a typo. This is 3S. Okay. Fine. So parent of A will remain S. Okay. So this doesn't changes. Then after CA we go to DC. Now again, weight of D at this point is infinity. Infinity plus 3 is not going to be better than C. C got the new value which is 15. So this became 15. Okay, so DC is 15. So D is infinity, DD is infinity plus 3. E is not going to be better than 15. It's not going to be less than 15. So it remains C. C remains at 15. What about ED? Now E in previous iteration it got the value 1. So 1 plus 2 E is better than infinity for D. So now this time D gets the value 3 and the parent of D is E. Then comes SA. So we are done with ED. Then it comes SA. S is having the starting value as 0. DS is 0. And A is 3. This edge weight is 3. So 0 plus 3 is same as whatever is already stored. So it's not better. So it still remains at same. A remains as 3S. And then comes SE. Fine. In SE, what happens? What is the weight of S? D of S is 0. 0 plus 1 is same as whatever is the current value of E, which is 1 here, already 1. So it also doesn't needs to be updated. Okay. So it remains at this. Fine. And then at this juncture, we are done with this iteration. I becomes 3. Now when I becomes 3, what happens? Again you go through the same sequence A, B. Now A is already 3. 3 plus 5 is 8. So B remains at 8. Okay, parent is still A. This should be S. Okay. BC. B is 8 plus 7 is 15. So nothing changes. Okay. So it remains at 15. Okay. Then CA. Now C is 15 minus 5 is 10. So A remains unchanged. DC. Now when I go to DC, now notice what happened. D value in the last iteration, it got 3. So DD became 3. DD is equal to 3 in the last iteration. So 3 plus 3 is 6, which is better than 15. So your C value should be updated to 6 and say the parent value as D. Okay. So 6D. Fine. Okay. So C gets updated because of DC. Now ED. ED is 1 plus 2 is 3, same as this. Okay. So it's not going to change. SA, you can verify, that is also not going to change. Same as SE, also not going to change. Okay, fine. Then we move to I is equal to 4. So this C value, if you notice, C value is not anymore 15, it is now 6. And that's the interesting part. Now what happens when I is equal to 4? Again, AB. AB will remain, A is 3, 3 plus 5, 8, remains unchanged. Okay, the B value. BC, B is 8 plus 7 is going to be 15, which is more than 6. So C remains at 6. CA, now CA is 6 plus minus 5, which is 1. Okay, and 1 is less than 3, so it gets updated to 1c. That means D value, so dA becomes now 1 and the parent is C. Okay, that means you have to come through the vertex C. Fine. Okay, so this becomes now 1. Okay, coming back to we finished with CA, then we move to DC. So DC again, D is having the value 3 plus 3 is 6. It is already 6. Okay, nothing needs to be updated. It is not going to be less than 6. Okay, so it remains okay, does no changes. Then comes ED. ED is also not going to create any changes. Okay, because E value is 1 plus 2 is 3. So D value remains at 3. Okay, what about SA? Now SA, notice that S is 0, DS is 0, plus 3 is 3, which is not going to be less than 1 because already DA is 1, right? This DA is 1. Okay, so 3 is not less than 1. So that doesn't need an update. How about SC? SC also, S is 0 plus 1 is 1 and E value is already 1. So that is also not lesser. So that also doesn't need an update. Fine. Okay. We move to the next iteration, I is equal to 5. Why are we going till 5? Because total 1, 2, 3, 4, 5, 6. 6 vertices are there. So V is equal to number of vertices is 6. So according to the algorithm, we should go from 1 to 5. So we are going to the last iteration, I is equal to 5. And now notice what happens. AB. Now value of A is what? DA is 1. 1 plus 5 is 6. So now I will update my B to say that okay, the DB value is now 6. And parent still remains A. BC. Now when I go to BC, now I have 6 plus 7, which is going to be 13, which is definitely not less than already existing DC value, which is 6. So that doesn't need an update. Okay. So BC is done here, and then CA. Now when I go to CA, C is already 6 plus minus 5 is 1. So that is not less than already existing value of DA as 1. So that also doesn't need an update. Okay. So nothing will change for CA. How about DC? D value is 3. 3 plus 3 is 6. 6 C is already 6. So that also doesn't need an update. How about ED? E is already 1 and 1 plus 2 is 3. Okay. So D value is already 3, so that also doesn't require an update. SA, S is 0 plus 3 is again 3, which is not better than 1. So A, nothing changes for A. Okay. SE, same thing, nothing is going to change for SE. S is 0, edge weight SE is 1, so 0 plus 1 is going to be 1, which is not going to change the existing DE value. And that's where we stop. Fine. That's what is Bellman-Ford algorithm. Now notice, if I have, now the question is, what is the shortest path to, let's say, vertex A from S? How do I find that? And the way to find is that, look into A and say, oh, the weight to go to A is 1. If we say that, okay, what is the shortest path from S to A? So first of all, total weight of the total cost of the path is 1. Okay. Well, not 1. Sorry. It is, let's see. The parent of A, what is the path? How do I reach A? I reach A via C. So I will, I have to reach A via C. Parent is C. How do I reach C? C is reached by the value D. Okay. So the parent is D. Fine. Okay. And then what is the parent of D? Parent of D is E. What is the parent of E? Parent of E is S. So the path to A is S to E to D to C to A. What is the cost to this path? S to E is 1, E to D is 2, D to C is 3, and C to A is minus 5. What is the cost? 1. Fine, the cost is 1, which is stored in DA. Okay, that's the cost of the shortest path. Okay, so the shortest path is not SA. Because of this minus 5, the shortest path is S to E to D to C to A. Okay, the cost of path SA is 3, which is larger than 1. Okay, what is the cost to path B? So again, if I have to find the path to B, what is the parent of B? A. What is the parent of A? C. What is the parent of C? D. What is the parent of D? E. What is the parent of E? S. So I'm going S, E, D, C, A, B. What is the cost? Already we have seen this much is 1 plus 5, that is 6. So that's the cost 6, which is stored in DB. Okay, fine. That's the shortest path to B. What is the shortest path to C? The shortest path to C, if I see, is, what is the parent of C? D. What is the parent of D? E. What is the parent of E? S. So the shortest path is S to E, E to D, D to C. That is also 6. And that is stored in C. Okay, D of C. Fine. So that's how we figure out, using Bellman-Ford algorithm, the shortest path to any vertex starting from the source S. So what is the running time? Let's see. For I is equal to 1 to V minus 1, that's the first loop. Within that you will iterate over all the edges, and every time you will say relax. So how many times the upper for loop will work? V minus 1 times. And for each edges, that means order of E, whatever is the number of edges. So that's how much time this upper loop will take. The other loop, which goes for finding the negative weighted cycle, will iterate over only the number of edges. Okay, so the total time is order of V plus order of E, or which is order of V. Okay, V times C. Okay, so that's Bellman-Ford algorithm. So we have looked into essentially the single source to all the vertices shortest path problem. Okay, how to solve it using Bellman-Ford algorithm. Okay, thank you.